All right, welcome everyone to the AI for damage inspection final presentations. This is a FruitPunch AI challenge uh, provided by the Dutch AI Coalition and ProRail, but most of all, we want to thank our partner Rijkswaterstaat, otherwise known as the Ministry of Infrastructure and Water Management in the Netherlands, for organizing this challenge with us. For today, we have a couple of presentations. First, I'll do the Fruit Punch introduction. Then Pierre will tell us about his team, who worked mainly on the Rijkswaterstaat data. And then afterwards, Roshan, Kembo, and Luiza will tell you their journey, mainly focusing on the CODEBRIM dataset. I hope Aria will still be joining. She wanted to do some closing words, otherwise I can do those as well. For everyone who wants to ask questions, please, if you have them during the presentation, you can raise your hand by clicking the hand icon in the bottom of your screen. And we can pause the presentation whenever that's best, and then you can ask your question. Otherwise, if you feel more comfortable putting in the chat, that's also fine, and I will read them out loud, and I will ask them for you. So who are we? For everyone who's unfamiliar with Fruit Punch, we are the global AI for Good community. And we do this because to solve humanity's greatest challenges, we need to educate AI engineers at scale with an ethical and sustainable mindset. Well, how do we educate AI engineers? We do that by challenge-based learning. We organize AI for Good challenges, which are geared towards the sustainable development goals. And through these AI for Good challenges, we educate a lot of people all over the world in a peer-to-peer manner. We organize them, for example, in the area of wildlife, oceans, clean energy, but also infrastructure, cleaner cities, you name it. If it's AI for Good, then we organize challenges for it. So one of these challenges is the AI for Damage Inspection Challenge. So for the last 12 weeks, we had two groups working very hard for over 900 hours in total on this problem. The goal of our challenge was to use computer vision models to allow detection of structural damage to objects in public space by drones. The main focus here was on concrete, and we've later even narrowed that focus down on specifically concrete bridges. And this challenge refers to the 9th and 11th Sustainable Development Goals of Industry, Innovation and Infrastructure, but also to sustainable cities and communities. As I said, the challenge took place over the last 12 weeks. We started with the kickoff, we had some educational master classes, and then started actually working on the challenge. Today you're here on the final presentation to see all the hard work that our AI for Good engineers put in. And as I said, if you have any questions, you can ask them after the presentation, but if you have them during, then please raise your hand. All right, I'm not going to take up too much of your time because most of the interesting content is coming from the teams. So I would like to give Pierre the floor to introduce their work. Pierre, I will stop sharing my screen.
All right, perfect. So, afternoon, everybody. My name is Pierre Le Roux. So the agenda for Team 1 is just to introduce the project, the team and goal, the problem statement and the impact of the topic, our solution directions and struggles, the results that we have, and then advice for the continuations and lessons learned that, going forward, that Rijkswaterstaat or anybody else who approaches this problem could use. So first things first, the team was Frank Thompson, who served the role as product owner, myself as a Scrum Master, Mohammed, who was a fellow team member with Timothy, who assisted in a lot of the work, and then in grey is Sri, who has been with us for like 75% of the project. And then so contributed a lot of the methodology and how we thought about it, but didn't complete the project with us in the end. He had some other life opportunities that happened. So the problem statement or the idea is that it's quite a manual task to inspect bridges, and it's quite difficult and dangerous. And to perform it correctly, you need to inspect the entire bridge from a close range. So it has already been proven, the idea of this challenge has already been proven, that capturing footage with drones gives us the opportunity to detect damages. The idea was to then see if we can improve on this original training that's been done on YOLO v3. So the solution directions for our team went into two directions. Number one, trying different algorithms with the original data set labeled OD. So different algorithms would be ConvNext, YOLO v5, YOLO v7, and then Detectron 2. And then the second approach was to enrich this original data set, and we call this the enriched data, or ED. So just keep in mind, we have OD and we have ED, original data and enriched data. So first off, the original data set, it was around 900 images. So 716 or 80% of that was used as training, 20% of that was used for validation. That is how it was set up as a base case. So we wanted to mimic this as close as possible. And in the enriched data set, we incorporated CODEBRIM data that is publicly available concrete that has been labeled to a certain degree. It's not the best labeled data set. It's one of the challenges we faced, that the publicly available data for this challenge isn't nearly labeled good enough. But we still applied this on our training to see if we can improve it. The base idea was to see if we can improve on YOLO v3, and we did show in different cases that depending on the data and how it's labeled, we can use new algorithms like ConvNext to improve this on the OD set. That is, like, we don't think that's a limitation. We'll chat to that again later. So we can see here that ASR by far is the biggest accuracy or precision. Skewer, which is like a crack, is much lower, and beton rod is in between the two. The reason for that is because of the representation, the amount of data that is in the data set, number one, and number two, also ASR is very biased in this case, where it's only from one bridge. So the entire data set is one color and one, most of those images that were provided are basically, the entire image consists of ASR. So it is a lot easier for the model to detect. So next on, we used YOLO v5 on the original data set and the enhanced data set, and we could see very good scores on ASR, almost close to 100% for the reasons that I just gave you. The enriched data set actually took it down just a bit. The reason for that is that the reason why the enriched data set doesn't really differ that much is because there's no ASR in the enriched data set. That's one of the limitations of the publicly accessible data. So so on skewer and beton rod, you can see YOLO v5 got really good results initially, but it went a lot worse with the enriched data set. And the reason why is we found that the enriched data set was not labeled as well. And again, you have much more variety. So maybe in the essence of that is you need to ensure that the amount of healthy concrete within a boundary box is limited as much as possible. So there's different approaches to that, but yeah, overall we did get an improvement only on using different models and not necessarily the enriched data set. You would have to, there's some recommendations coming soon. So that was for the OD versus ED on our precision and recall, and then over the mean average precision for the two data sets. Like I've mentioned now, the original data set with YOLO v5 gave us the best results, just because of, again, that sort of, it doesn't show that the enriched data set is necessarily bad. It just shows that once you take this model and give it a variety of bridges and a variety of scenarios, the amount of accuracy greatly diminishes. So again, why ASR is well represent or good, like has a good average precision, is again because it's only represented in one bridge. So it didn't confuse the other images as ASR, so it was good in its training. But we can see the crack, betonrot, both decreased significantly. So that means again that the amount of healthy beton is being judged as cracks or betonrot, depending on the data set and how good it's labeled. Then we also trained it on YOLO v7. And again, so YOLO v7 had a bit lower results in the original precision for the original data set, and it improved significantly with the ED data set, so probably confusing less of the ASR. And yeah, there was some improvement on YOLO v7 for the enriched data set, which was interesting to see. So maybe some of the algorithms are better at identifying the issue within the boundary box. So we found like YOLO v7 might be a better algorithm to use once you have a bigger data set of a variety, and maybe just tweak the boundary boxes a bit to include less of the healthy beton. But we found that in some cases it does actually do better than the original data set, which was a sort of a unique trait to YOLO v7. And yeah, this is just again the mean average precision for that same data set. So once you go to the average precision, it does decrease slightly or stay the same. I think the only one is cracks are quite well represented in the enriched data set, but some of them include, again, like I mentioned, a lot of healthy beton, a lot of healthy concrete. So it really struggles with that. So here's just the ground truth. So you can see like the ASR that I mentioned, like all of these images look basically the same. All this yellowish color with the ASR symptoms that is identified, and almost the entire image is just classified. Where some of the other images, so you can see here's like a crack and betonrot, there's betonrot, here's apparently betonrot, and these are all cracks. But as you can see, like a huge portion of this looks like healthy concrete, but there's like a hairline crack there on the side. So the model basically like identifies a lot of this as different like cracks, although much of it could just be like healthy concrete. And of course, again, the ASR was sort of the easiest to recognize because it's the same color, it's the same pattern. And yeah, in some cases, it wasn't even able to identify betonrot because that line is so, it's very underrepresented in the data set. And then the Tictron on the enriched data set did a bit worse between YOLO v5 and v7, but the assumption or the conclusion that we came to is that the Tictron will, although versus the other models, it does worse now. If you have a much larger data set, it will be more competitive than the other two models. It needs a bit more to get to that point, but once you have data set that's more representative of each class, it will actually outperform both the others. But for now, it's slightly worse than YOLO v5 and YOLO v7. And yeah, here we can see just again like the ground truth. Here's like betonrot and skewer. So that's again concrete rot and cracks. And then here the Tictron detecting most of the betonrot, but some of the cracks not picking that up. Again, so yeah, YOLO v5 picking up the betonrot, not all of it again, and then YOLO v7 like just labeling the entire section as betonrot. So the advice for us from our team for the continuations and the lessons that we learned is actually the portion that we want to get to, is, although there's various models and there's various ways to use them, across the board, all of them would show slight improvement to the YOLO v3, even on the original data set. But the biggest thing was that you need diversity throughout the classes and throughout bridges. So in terms of ASR being represented only in one bridge, it might, like, once you get a bridge with ASR that's gray, it would not be able to detect it, for instance, because it identifies this yellows pattern as ASR very strongly, because it's just represented by this one bridge. So you need about 1,000 quality annotations of various per damage type. So about 3,000 images in total if there's 3 damage types. If there's more, like in the CODEBRIM dataset, we have like exposed bar as one of the data classes and stuff like that. So 1,000 quality annotations for each class would give a much better representation. And then if throughout those if throughout the 1,000 images, they can be like 5 to 10 different bridges. So if you have a class and you have 5 bridges, around 200 image per bridge per class, if that's possible. Like, again, I know not all bridges will have ASR, not all bridges will have betonrot, but the variety of the color of concrete, the time of day, and the size, and then getting labeled data is going to be the biggest contribution. So as we mentioned in our intermediate presentation, that the data provided is very limited in the volume, the diversity, and the quality. For the training, that's the 900 images that we used. So there is I think Rick Waterstad has a lot of data that they can label, and if they spend time accurately labeling those data sets, it will significantly improve any model that they choose. From our recommendation, V5 or V7, or then even if Detectron 2 can be used to improve the score if you have, again, that significant amount of data. So yeah, that is sort of the conclusion from our side. Any questions?
All right, thank you, Pierre. Let's open the floor for questions indeed. Otherwise, I'll have one. Comparing the YOLO V7 and the YOLO V5, like how much better did the 7 was better, right?
Yes. So sorry, just give me a second. So 7 in some cases did improve it. So how can I say this? We actually don't have a result V5 versus V7 directly. It did slightly improve it and actually did a bit better in some of the cases with the enriched dataset, which was interesting. So it was the only model that would actually it slightly detected the cracks and beton rot better, or the concrete rot better on the enriched dataset than YOLO V5. So we're thinking that it better accounts for the background in the boundary boxes. So it might account for that sort of error in the human labeling a bit better than YOLO V5.
Okay. All right. Any other questions?
Well, from me, maybe.
Sure.
Thank you at first for your great work. We truly appreciate that. I have a question about the different types of concrete or materials, because we also have a lot of steel bridges. Can we use the same model also for a steel bridge?
I'm assuming in the steel bridge you would have concrete parts to identify, because I mean currently it would be able to identify a crack on concrete. I don't necessarily think it would be able to identify a crack on steel. And I don't know. I don't think the class type concrete rot or beton rot as you exists on steel. So it would like rust. So it's a better. It would be a new class to to train and identify. But the same models could be used given labels for those classes. So if you have images of a steel bridge and you have damage types on those steel bridge, that is something that can be added, definitely.
Okay, thank you. That's nice. We've got a lot of work to do, I guess.
Yeah. I think if you have a quality inspector and somebody who can do labeling, and you can take the learning from the inspector and give it to the labeler in terms of understanding how a damage type looks. So meaning if a labeler has 4 or 5 examples of each data of each damage type. So it doesn't necessarily needs to be a professional, but if the labeler has some reference that he can, like, okay, yeah, this looks like beton rod, this looks like crack, this looks like rust, this looks like ASR, and they can label the data sets that you guys already paid for to get in, that would significantly improve any model that you choose.
Yeah, okay.
Yeah.
Thank you.
And there are a lot of companies around who do this labeling. So if you're willing to pay a bit, then it will save you a lot of work.
Yeah.
All right. If there are no more questions for Team 1, I'd like to continue with Team 2.
Thank you very much.
Thank you, Pierre.
So basically, the team is me, Roshan, Varun, Jerry, and Sarah, who could not be here. We tackled the problem with three goals. The first goal was a binary multi-label classification in conjunction with a learning curve analysis, which would be useful for detecting multiple instances of defects within a single image, and also to provide an estimate of how many training samples we need to have a robust model, at least for classification, which could be a bit simpler than object detection. Then there's another goal, which is object detection. This is all using the CODEBRIM datasets, just to be clear here. And the third goal is the multi-class single label, which would be useful for inferring the defect label of a cropped image with a single defect. So the binary multi-label classification, it is binary because each of the labels can have either the value 0 or 1. So basically no damage or damage. And there are 5 kinds of damages that we added to the dataset. We kept in the dataset, actually. And just explaining what the learning curve analysis is. The learning curve analysis, we train different models with increasing training set sizes, and then we measure their performances both with in-sample and out-of-sample dataset. The out-of-sample is fixed for all models, and the in-sample size is what changes. In the end, we have a graph that is basically the training set size on the x-axis and a desired metric, a metric of interest in the y-axis, which in this case, we use the F1 score macro averaged. And the goal here is to assess the generalization performance of each of the models and understand the minimum number of training samples necessary to achieve a good enough performance on that out-of-sample data the model did not have access to while training. And it also could provide us of an estimate of, do we need even more data based on the curve's trend or something like that. The dataset here, like I said, is a CODEBRIM. We use the original CODEBRIM object detection dataset, and we just modified the labels to a binary multi-label classification task. There were 5 labels initially. 6 labels initially. One of them was the background, which we removed from the data. And we applied minimal transformations to the data, which were basically resizing, random crop, and the normalization the model required. The model we used was a pre-trained vision transformer with 384 pixel input size. And the train validation and test splits were stratified based on the multi-label classes. And this was applied for all of the splits during the training and evaluation, just to make sure all of the classes are represented in all of the splits. Like I said, I held out a test set initially of 152 samples. This test set was used to evaluate all of the models. And in total, 5 models were trained. The initial idea was to train 9 models from 100 to 900 samples, but then I kind of ran out of computing resources and decided to reduce the experiment. So I just did the 100, 200, 300, 400, and 900 training set sizes. And another thing is that the training set size actually is 80% of the value, because 20% of each training set size was held out for validation and early stopping and checkpointing and stuff like that. So basically the model trained with 100 samples was actually trained with 80 samples and validated on 20 samples. All of the models were fine-tuned for 20 epochs, but the best checkpoint was saved based on the validation F1 score. These are the results. So the best model, like expected, was the one with the most samples. So with 900 samples, we achieved basically a 98% training F1 score, and an approximately 82% test F1 score, which is a 16% gap between those sets, which kind of shows us that we still have room for improvements here. And this is the results stratified by class, the F1 score by class. Most of the classes maintained an 80% F1 score, except for the efflorescence one. These are the 5 classes we have in the table and in the image. The efflorescence one was also the one that had fewer samples. So yeah, that's basically it. And the takeaways here are that I think a question we had during the experimentations was of if pre-trained models would be of any help for this problem, because the pre-training is usually done with ImageNet, which is a very different data set from concrete images. And I believe so. I believe it helped a lot, and we were just able to achieve about 80% of F1 score due to the pre-training of the model. Another guess I would probably have is that increasing the input size would help the model to accurately detect more damages. As you can see in the image in the screen, there are a few damages which are very small, like this exposed bars ones. So maybe a larger resolution image would prevent any loss of information. And I guess the most clear takeaway for me is that we would benefit for more data or even an aggressive data augmentation with this training and validation sizes, kind of corroborating with team 1 in this aspect. And that's it. Go to Kembo. Varun, are you there?
Yeah.
Okay.
1 second. Yeah. So just to reiterate, for object detection, the goal was to understand the location of specific defect instances that were found in a particular image. Here, we used data from both CODEBRIM and RWS, and the classes were because the 2 data sets were different, we tried to unify the classes. So here we just have 3 classes, ASR, SURE, and Button-Dot. For the model, we used pre-trained YOLO small. Just to simplify things, what a checkpoint means is, in simple terms, it's just a group of weights that defines a nonlinear function. So what we do is we give inputs to this nonlinear function, and we get a vector representation of an image. To look at in a different perspective, what these weights represent is the knowledge that was gained from training on millions of images from a different domain. And that knowledge can be useful to help us with object detection in our case. So once we get a vector representation of the image, the damage image that we have, we pass that into the ATR model, which is object detection end-to-end with a transformer model. So if you look at this, it has 30 million parameters. It does seem pretty large, but look in comparative terms with other language models that we see in today's machine learning advances, those are almost billion parameters size. So in other words, this is still a relatively small model that we can use to do object detection. So looking at the split of the data sets, so we had about 1,200 images for training, 400 for validation, and ultimately we tested it on about 260 samples, and we fine-tuned these for about 10 epochs. Once the training was done, we got an average precision of about 0.36, which is 36%, and average recall was about 49%. Looking at the takeaways, we did the size of the annotated data set was relatively small. What this means is pre-training with large transform models is still a better option compared to training the entire neural network from scratch. Also, if more compute is available, we can potentially explore even larger pre-trained models, something on the order of hundreds of millions of parameters as opposed to just 30 million parameters. And it can lead to better feature extraction. When I was training, I only had access to one GPU. So that's why I had to limit my training to a smaller yellow small model. Also, because large pre-trained models are available today, we can prioritize the quality of annotation rather than trying to get lots of data. So even if it's small amount of data, if we can have very good quality annotation, then I think with the help of large pre-trained models, we can still achieve a very good performance. Over to you, Roshan.
Okay, hello all. My name is Roshan. I'm part of Team 2. Yeah, so Team 2 worked both on object detection and multi-class classification, and we also worked on multi-class single label classification. So given an image, there is only one defect, and how do you go ahead and classify that was the main focus for me. So, well, I used both the dataset, RWS and CODEBRIM dataset. RWS dataset, as all of you know, it was around 850 images, 179 for validation, and 3 defect class. The most interesting part was the CODEBRIM dataset with around 2,600 images for training, validation something around 278, and there were 5 defect classes. And this is the distribution of the training samples per classes. Same goes with the validation. This was the distribution of images per classes. A little bit on the data exploration. As you know, the RWS dataset had fixed width and height pixel representation. But with the CODEBRIM dataset, the variation was quite large, as you can see here. If you do the k-means clustering on the right hand side, you can see 4 diverse group with large variation in the image width and height. Pre-processing was fairly simple. Mainly the image were parsed based on their appropriate classes or defect classes and were placed in the appropriate defect folders. Neural networks require input images to be of appropriate dimensions and normalizations. So these were the only pre-processing done. For the modeling, 4 neural networks were used for training on CODEBRIM dataset, and only simple CNN model was used for RWS dataset. And the total parameters, trainable parameters for each model is, as you can see in this figure. This was the architecture that I used for the RWS dataset, a very simple textbook example where you have 3 stages, of the network. This was slightly changed model for CodeBRIM dataset. Again, textbook example for the AlexNet. The biggest model to understand was the ResNet 50 with 4 or 5 different blocks. And same goes with the, AlexNet architecture. Coming back to the result, as you can see, for the cracks or skewer, you have F1 score of 0.5 and rest it's 0.3. On the right side, you can see how was the training and validation accuracy and training and validation loss. You would say that is overfitting even for the simple model. But this is what I got for simple neural network with 10 epochs. This is the result for CodeBRIM dataset training and validation for 10 epochs. This was the last accuracy of the model. So more or less it is on the same line. But if you can, if I can draw your attention to the simple CNN, you can see that, yeah, it learns better than any other models, maybe because of its simplicity. Other models are way too complex and deep in its architecture. This is the classification report for simple CNN on the CodeBRIM dataset. Yeah, for some reason, efflorescence and spallation was, I didn't get any F1 square, but cracks, as you can see, has got the highest F1 square, F1 score and recall. For the ResNet is again the same. Cracks is having the highest score. Next to, I think, corrosion stain. AlexNet, again, it's cracked because we have more number of samples with the cracks in the data set. And last but not the least, for the exception, and in most of the cases, exposed bars is 0 because the number of data samples that we had was very, very less compared to any other data set. This was something really crazy for me. What I did was, of course, I did use all these models, but the first test was, how about just using, ResNet 50 exception model on a pre-trained image data set without any fine tuning. So these were some of the images that I gave for ResNet 50 model that is pre-trained on ImageNet. You get some really crazy results. Like these are the crack samples, but the ResNet 50 said, I'm detecting 21% ant, some bee eater and stuff like that. So I don't know if pre-trained model can really help. So I didn't do any fine tuning on any of these models. I just used the model as is based on the pre-training on the ImageNet dataset. Yeah, so these were the things, and hurdle for me especially was to understand the neural network architecture. You can get the result, but how does it really work? That's the key issue here. And interpreting the results, I mean, you can see that FN score is around 0.38, 0.58, but taking that individually may not be a right way. As you can see in the diagram here, these are the different ways you have to use to say whether your results are good or bad. So interpreting the results were sometimes very tricky for me. And of course, more number of people means we can do more better things. So unfortunately, we were only 4 to 5 members within the team now. Well, takeaways, well, large deep models may be an overkill if the data set is too small and with lesser number of class labels and small variation in the data set, definitely it can lead to an overfit. Transfer learning may or may not help if the data is not trained on a specific data set. If you do have smaller data set, then instead of going for very deep learning models, perhaps we could use something like few shot learning. It makes sense when the data set is small. Yeah, more fine tuning may increase the accuracy of the model. More images will definitely improve the accuracy of the model. Last but not the least, thanks FruitPunch AI and RWS for giving this opportunity. I at least learned a lot. There are a lot of things that I missed, a lot of mistakes made, a lot of things to learn, but it was fun. Yeah.
Nice. Yeah, that's also very important. Thank you, Roshan. Good presentation. Also, thanks to Kembo and Luiza. I have a question. The ResNet and the AlexNet, did you use pre-trained weights for those when you're?
For these ones, no. I just trained everything from the scratch. And that is the result that you see here in all of those.
Yeah.
But in this one, what I did was, there were already pre-trained models on the ImageNet dataset, and I just gave these, images like beton rot and cracks to already pre-trained models and saw what is the prediction accuracy of those models.
Yeah.
So yes, I tested on both scratch and also pre-trained on ImageNet dataset.
And can you go back to the slide where you show the basic CNN performance? Because I'm
This one?
curious how well that. Yeah, I think it's pretty funny, right? That a simple CNN with what 2 hidden layers performs as well as and even better than ResNet and AlexNet and everything.
Yeah, so the thing is with the simple CNN, what I did was I used data augmentation as well, but for others I didn't use data augmentation. That's the only thing I tried to do. Yeah, I checked my code again and again if I have done anything wrong here to see if it really is. Did I mess up with the code or is it really the case? Try to fine tune with different epoch size and but more or less I'm getting the same result after multiple runs.
Yeah, I think one of the explanation indeed is that if there's not that much variety in the data set, then a simpler model is probably a better choice.
Yeah.
Nice. I'm curious about Team 1. How did you maybe also see a relationship like this, like that simpler model would perform as well?
On my YOLO v5 training that I did, I found that the small model versus the X model diminished the scores. So I have a fairly beefy GPU in my computer, so I was able to train on the YOLO v5 X model, and that definitely gave me the best results out of YOLO v5. So I found an improvement as I increased the pre-trained model size.
Yeah. Okay. All right. One more question. The test set that you used for this set, is that the same test set as Team 1 used?
Yeah, so I used the one for RWS. I used the one that was called train and validation. It was not from the original data set. I used those. And for the CODEBRIM, there was already a test images already available.
Okay.
I see that there was another question someone asked.
Oh yeah, in the chat, Jeremy is asking about the augmentation techniques.
Yeah, that's a good question. Just let me see my code if I've opened it. I have so many windows open here. Yeah, so it was basically resizing the images, adding some noise. That's the only thing that was done. To be make sure. Let me go to the code and see. Yes, the shear range was 0.2, zoom range was 0.2, and horizontal flip was equal to true. So I used TensorFlow, a basic data augmentation there.
Right. All right. Okay, thanks. Yeah, I think you can stop sharing your screen if there are still any questions left. Cool. All right, I think then we've come to the end. So yeah, first of all, I really want to thank everyone for spending their hours and hard work into this challenge. It's very much appreciated. We know you all guys are all volunteering your free time for this. So yeah, do know that we appreciate it a lot. Besides that, I hope that you learned a lot as well. And I hope that I can, or that you join more of our FruitPunch challenge, because I love to work again with you in different projects.
Yep.
Yeah, thanks a lot, guys.
Thanks so
Alright.
much, Dorian. Thanks so much.
See you
Aryan.
guys. Bye.
Thank you all.
Bye.
Have a fruitful evening.
Yes.
Thanks so
Thanks so
much.
much. Thank
Ciao,
you.
ciao.
Bye-bye.